unaffected. And we chose this leaf at bud break or 5th week in development to assess the nutrient status of these crops. And this is typical of the industry. And in this case, the N level in the leaf was 4.5 to 5.5% dry matter. The phosphorus level 0.22 to 0.26 or 62% dry matter, and the potassium level 3.3 to 5.6% dry matter. And as you can see, these are within, we consider the acceptable limits in comparison to the extension literature. And in this case, I'm using the OMAP for publication 370 and information from R.J. Hill Laboratories Limited in the US. So this brings us to our current project, which is to optimize the delivery of calcium and magnesium, as well as the micronutrients and sub-irrigated and drip-irrigated systems. As above, we focused on removing the nutrient supply during vegetative growth in combination with the removal of the nutrient supply during reproductive growth, and nutrient status was assessed using the diagnostic leaf at bud break. Unlike my previous seminar, webinar presentations, I'm not going to show you the detailed results from each experiment because generally we don't see any effects, as you may recall, but rather I'm going to show you how far we have advanced our delivery system today. And so the objective in the first objective was to look at the calcium magnesium supply. And in response to the commercial trial, which I pointed out above, this Schenck MPK, Schenck adopted, and at that time, Schenck was using this Peters professional fertilizer, and they adopted a fertilizer rate at 100 ppms of nitrogen, which the Schenck, what I'm calling Schenck standard. And this has 18 ppms of phosphorus, 100 ppms of K, and so on. And they used this successfully for at least a couple of years with excellent results. In our research trials, which I'm calling calcium 1 and 2 here, University of Guelph, magnesium 1 and 2, the calcium level was reduced by about 60% with comparison to the Sonnefeld, and the magnesium about 85% in comparison to that. And then we also conducted a trial at the university, which we lowered the NPK levels to the lowest we've used in all our trials. This is 64 ppms of nitrogen, 20 of phosphorus, and 90 of potassium, in conjunction with these lower magnesium and calcium levels. And about this time, Schenck's adopted, this is last summer, adopted this Fusion Plant Products as their fertilizer. And this is actually at 100 ppms. And as you can see, this has some even lower levels of calcium magnesium. So when we decided to incorporate that into our program, and we did a commercial trial at the farm last summer. So these are indeed pretty low levels of all the macronutrients. That's in the blue box right at the bottom of the table. In our research trial, essentially the general characteristics of the plants were unaffected by either the magnesium or calcium level. And this is just a typical picture from that trial showing the two cultivars. And then in the commercial trial, we used 4 different cultivars, and there were once again, no effects, despite the serious decline in the nutrient supply. And the leaf macronutrient composition also indicates that in these 4 trials that the calcium magnesium levels are all within the range, the acceptable range found in the extension literature. Then we shifted at this point, we shifted our focus to the micronutrients. And this slide shows the same fertilizers I showed you above, but this is the micronutrient composition in chronological order from when we used it. And we first examined the zinc and copper levels, and we used the zinc and copper levels that were 1/5 the level in the Sonnenfeld solution, which, as you can see, is lower than any of the other commercial fertilizers. And once again, these are some general pictures from the trials, but there were no effects on the plant and flower yields, and the quality was unaffected. And there were no visual symptoms. And the leaf and micronutrient composition of the zinc and copper were generally within the levels that we consider acceptable. There was one exception: the copper was marginally lower, but since we saw no symptoms, I would rate this as acceptable. In a third objective, we looked at the manganese and iron supply. And so far, we've completed only one of the trials. You notice we did 2 trials with each of the nutrients above. We've only completed one of the manganese and iron trials so far this year, but so far we've lowered the manganese level from 0.27 ppms in the Sonnenfeld down to as low as 0.069 with ppms with no issues. So we're now lowering it as low as 0.017 ppms, which is a quarter, down to 25% of the level we're currently using. And with iron, similarly, we've gone from 1.4 ppms down to 0.015, 0.15, and again with no issues. So we're going to go down to 0.037 in our current trial. I mean, previously we have replicated each trial twice, but since it's getting a bit discouraging when you can't see symptoms, one it gives the impression that you can't do experiments. So we're doing so in our replicate experiments. We are making an attempt to lower the nutrients again if we do not see symptoms in the first trial. So in this particular trial, we found no symptoms of deficiency, and the characteristics were unaffected. This is the manganese trial on the left-hand side and the iron trial on the right-hand side. With the iron trial, we had problems with our blinds that control the day length, and so we had to repeat this experiment. And at that time, there was only one cultivar available, so that's why all the plants are white rather than red and pink as on the left-hand side. And in this trial, we found manganese levels and iron levels that were easily within the acceptable range found from the extension literature. The next objective then is to look at boron and molybdenum delivery. And the first experiment we've done this summer using boron and manganese levels, molybdenum ranging from 0.05 to 0.13, and that's for both boron and for molybdenum. And the second experiment we conducted in winter 22, either repeated if we see symptoms, but if we don't see symptoms, we'll lower the boron levels and molybdenum levels even lower. So together, these studies of the micronutrients as well as the macros will be used to design the optimized nutrient regimen for the final commercial trial, which will be conducted in the summer of 2022. This is essentially it. Here in the yellow box, we've pretty well established the macronutrient composition that we will use, but we still have the final experiments to do for the micros. So we feel this, so far this research has shown that the nutrient use efficiency can be dramatically improved by reducing the supply of macronutrients, as well as zinc and copper during the vegetative growth, in combination with the removal of the entire nutrient supply during reproductive growth. Delivery of these nutrients can be reduced by 85 to 95% over the crop cycle compared to common industry solutions, without sacrificing plant and flower quality. With our first trial, we found similar findings with manganese and iron, and the second trial is ongoing, the replicate. We expect from this research that we will provide new knowledge related to the timing and supply of fertilizer to both sub-irrigated and drip-irrigated mums, and that the nutrient strategy will reduce the nutrient usage, the volume of nutrient-rich feed water that must be treated and or discharged, and the environmental risks, particularly with nitrogen, phosphorus, boron, and molybdenum. In future, we hope that this strategy can be applied to other floricultural crops. In the past year, Sky Duncan Stevens completed her master's thesis. It's number 4. And we published 4 papers in the Canadian Journal of Plant Science and 3 papers and 3 articles in the Greenhouse Canada magazine. And as you can see from the bold letters, several of these articles have attracted some attention. This research was funded by COHA and the Government of Canada, and our industry partners are Schenck Farms and Greenhouses, as well as AgMedica Bioscience. With that, I'm happy to answer any questions.